Hey everyone, ready to dive into some seriously cool research. Today we're tackling language learning, but not the kind with flashcards and grammar rules.
Note, we're going way deeper than that.
Think brainwaves, AI algorithms, and the surprising overlap between the two.
You've sent us a fascinating paper.
Yeah, this one really caught our eye. It's all about how our brains and cutting-edge AI, specifically a type called a GAN, process the sounds of language.
And what's really cool is they use this technique, CABR, to see what's happening in your brainstem, like in real time.
It's like listening in on the symphony of neurons firing as you try to decipher what someone is saying.
Exactly. They're comparing that data to what's going on inside a GAN, which is a kind of AI that learns by basically competing with itself.
Okay, I have to admit, I'm intrigued, but I think we need to pump the brakes for a second. Brainstems, GANs, CABR. Let's break this down so everyone's on the same page.
Absolutely. So, imagine you've got this big question. Do our brains and AI process language in similar ways?
Makes sense so far.
This research takes that question and focuses it on a very specific thing called peak latency.
Peak latency. Sounds like some kind of technical jargon.
It sounds fancy, but it's actually pretty straightforward. Think of it as the time it takes for your brain to react to a sound.
So like if a dog barks, peak latency is how long it takes your brain to go, whew, what was that?
Exactly. It's a tiny but measurable delay that tells us a lot about how our brains make sense of the world of sound.
Okay, I'm starting to see the connection here. We're talking about the speed of sound processing in both brains and AI.
Exactly. And this research uses that concept of peak latency to explore how our brains and AI handle a crucial part of language called voice onset time, or VOT.
VOT, huh? Not exactly something that comes up in everyday conversation.
Maybe not, but you use it all the time. It's the difference between bat and pat, time and dime, that tiny puff of air at the beginning. That's VOT in action.
Oh, wow. You're right. I never realized how much work my brain's doing in the background just to tell those sounds apart.
It's incredible, right? And it turns out that different languages like English and Spanish have different rules for how they use VOT.
Fascinating. So we've got two languages that handle sound differently, this concept of peak latency,
Yeah.
and then there were those AIs you mentioned. How do all these pieces fit together in this research?
Okay, buckle up, because this is where things get really interesting. They trained separate AIs, those GANs, one on English and one on Spanish, and then played them.
Wait, hold on. You can't just casually mention training AIs like it's no big deal. How do you even begin to teach an AI about the nuances of human language?
That's a great question, and it's actually what makes this whole study so mind-blowing.
Okay, you've got my attention. I'm ready for my mind to be blown.
So imagine these GANs are like the ultimate language apprentices, soaking up all those subtle sounds and rhythms and rules of a language.
But instead of boring textbooks, they're devouring massive amounts of audio.
Exactly. They trained one GAN on a ton of English speech data,
Okay,
and a separate one on a ton of Spanish speech data.
makes sense. So they basically become fluent, but how do you test that, especially if you're interested in this peak latency thing?
All right, so here's where it gets really wild. They created this kind of linguistic chameleon of a sound.
A sound, like one single sound.
Yeah, it's designed to be ambiguous. Depending on your language background, you might hear it as a ba or a pa, like right on that edge.
Ooh, that's clever. It's like a sonic Rorschach test for language. I love it. But how do you actually measure what's happening inside the brain when someone hears that sound? That's where the CABR comes in, right?
You got it.
It's like having a window into those split-second reactions happening in the brainstem as it tries to make sense of, hold on, was that a ba or a pa? My whole understanding of this word hinges on this tiny difference.
It's pretty amazing stuff. So they hooked up a bunch of English and Spanish speakers
Okay.
to the CABR,
Right?
played them this ambiguous sound.
Gotcha. And I'm guessing they did the same thing with the AIs, but how do you even begin to compare the inner workings of a brain to lines of code?
Well, that's the beauty of this research. When they looked at the CABR data from the human brains
Yeah.
and the activity patterns in the AI's convolutional layers,
Hold on. Convolutional layers, those are...
think of them like the processing units of the AI.
Okay.
The things that are actually analyzing the sound, what they found was shockingly similar.
Wait a minute. You're telling me that the way our brains react to sound, down to the timing of those reactions, looks eerily similar to what's happening in these AI models? That's insane.
It's pretty mind-blowing, right? And it gets even wilder. Remember how English and Spanish use VOT differently?
Yeah, it's all about that little puff of air.
Right. So when they looked at the CABR data, they saw a distinct lag, like a tiny delay.
A delay. Between what?
Between how quickly the English speakers responded to that tricky bapa sound and how quickly the Spanish speakers responded.
Oh, interesting. And the AI, the genians.
Here's the kicker. The genes showed the same pattern. The English-trained AI mirrored the English speakers,
No way.
and the Spanish-trained AI mirrored the Spanish speakers, even down to those tiny timing differences.
So not only are these AIs processing sound in a way that's structurally similar to our brains, but they're also capturing those subtle ways that our brains are shaped by the languages we've learned. That is absolutely wild.
It really is incredible, and it opens up some huge questions about the nature of language and learning.
Absolutely. But before we dive into those big picture implications, let's zoom back in on these GANs for a second. I have to admit, the whole concept of a generative adversarial network still sounds a bit like something out of a sci-fi movie. Can you break it down for us in a way that even our non-AI friends can appreciate?
Absolutely. Imagine a counterfeiter trying to create fake paintings.
Okay, I'm picturing the beret and everything.
And then you've got this art detective who's trying to spot those fakes. That's the basic idea behind GANs.
Okay, so we've got this AI art forger trying to pass off a fake Van Gogh.
And our AI art detective is laser focused, looking for those telltale brushstrokes.
But how on earth does that help an AI, even a clever one, understand something as complex and nuanced as human language?
So with a GAN, you have these two parts. The generator, which is like our master forger, and it's constantly trying to create these realistic outputs.
In this case, speech.
Exact.
Okay, that makes sense. And the other part?
The other part is the discriminator, which is our art detective,
Right.
trying to figure out, is this real speech
From a real person?
or is this AI-generated stuff?
So it's like a constant back and forth. They're
Yeah.
trying to outsmart each other.
Yeah, it's this adversarial process, and that's where the magic happens.
Because they're pushing each other to improve.
Yeah, the generator gets really good at creating this super convincing speech.
Okay.
And the discriminator, on the other hand,
Yeah.
gets really good at spotting the fakes.
So it's like iron sharpens iron, but for AI. Love it. But this research wasn't just about ba and pa, right? You mentioned something earlier about the AI actually mirroring the structure of the brain.
You're totally right. They wanted to see what was going on under the hood, so to speak.
Yeah, peek inside the AI's brain.
Exactly. They started visualizing what was happening within these convolutional layers.
Okay, I know we've thrown a lot of terms around today. Convolutional layers are what exactly?
Think of them like an assembly line.
Okay, I like assembly lines.
Yeah, so in this assembly line, the raw sound comes in one end.
Gotcha.
And then each layer, each station, does something to process that sound.
Okay, so if the first station identifies the raw sounds, the next station might be figuring out how those sounds fit together, like if it's a word or a sentence.
Exactly. And it just keeps getting more and more complex. And what absolutely blew my mind was they found this direct correlation between those layers in the AI and different stages of auditory processing in our brains, like
Right.
how we actually hear and make sense of sound.
So even though we're talking about silicon and algorithms versus this biological organ that's been evolving for millennia, at some fundamental level, they're structured similarly.
It's incredible, isn't it?
It's like saying that the best way to design a spaceship is to study the wings of a bird.
It's like evolution stumbled upon a similar blueprint for processing this complex world of sound, and that's huge for the future of AI.
Absolutely. If approaches like Jan's, which try to mimic how we learn, actually tap into some fundamental truth about intelligence, who knows what we could create?
The possibilities are really endless.
This research is really just the tip of the iceberg, but it's exciting to think about all the questions it opens up.
And the answers we might find as we keep exploring this space where language, brains, and AI intersect.
On that note, we'll leave you with one final, slightly mind-bending thought. If we can create AI that learns like us, what does that tell us about the nature of learning itself? As always, thanks for joining us for this deep dive. If you want to learn more about this research, check out our website for links and additional resources. Until next time, keep those brains buzzing.